Dearest friends, today we are going to start a review of the material, and because next week is a very special week, we call it the finals week, and in that week, of course, you are going to show all the educators on campus how great a person you are. Time to get those A's, right? But let me give you some information about our exams that may be helpful. So first, this class is evaluated. Every class of UCI is evaluated through this curriculum system. I think you have gotten an invitation to fill out a questionnaire. It's rather long, I mean, somewhat long, but it's actually very useful. And these evaluations are taken quite seriously. In fact, every time my performance is evaluated by my department chair, we have all these stats, all the comments that are made by students and the scores. And if it doesn't look good, he's gonna smack me. So it's serious stuff. It's not something that should be taken lightly. And so fill out your impression. If you like it, if you don't like it, you can just fill out what you thought your experience was. Okay, in addition, next week, Laura, one of the TAs, has kind of generously offered to do a review session. Next week, of course, there are no official classes, so this is an extra review session in this auditorium, okay, so this place. It's at 7 o'clock on December 10th. And so she will be at your service to ask her questions, and just like we've done before, we do it again. Unfortunately, on Monday, I'm unable to be here. I have a very important engagement in North Carolina at Duke University. I have to be there. So I cannot do it myself. That's why Laura is stepping in, and she's highly qualified to do that. All right, so December 14th, it's on a Friday. It starts at 1:30. Like I said, the exam will be 2 hours in total, so it's much longer than the midterms, and that means there's a little bit more breathing space for approaching questions, and you can look over your answers probably several times and be sure you give your best possible performance on this exam. So I'll send you more information. Again, we have allocated seating, so keep an eye on the website, the class website. All the information will be there, will be posted. The practice midterm has already been posted, by the way, so you can already start looking at that. Yes? The practice exam has been posted. Yeah, I just said that, and it's you can just go there and look and to get an idea of how long the exam will be, what kind of questions you may expect. As I said, it's going to be slightly different, but this is a very good impression of the level of difficulty, the length of the exam. Things to bring, as usual, an index card, your calculator, cell phones, we don't like so much, so leave them in your bag, turn them off. Okay?
Do we get 2 index cards or just 1?
Oh, very good question, people. How many index cards can you use? The answer is uno. Okay. And that is same as before. So this is not because we have 2 midterms, now we can have 2 cards. 1 card. Okay? So you can use that wisely. Some people write very beautifully with fine liners and they do a great job. Other people just print it out on a special printer and also do a great job. That's fine. Okay? Just don't have multiple layers that you flap open. That's not allowed. Okay. So this is the list of topics. There's nothing new about this. I'm just going to do it for formality's sake. Everything we have talked about is going to be on final. Final is truly a cumulative kind of exam that basically considers the entire course in its entirety. And these are the things that we talk about. Basically, if you like the book as a main source, it runs from chapter 1 to chapter 4. Okay? That includes the following topics. Dealing with numbers, okay? Sig figs, units, prefixes, and so forth. Dealing with numbers, writing numbers in scientific notation, is part of this class. So you should do that on the exam. Even if it's not explicitly stated, you should do that because it's part of this exam. Unit conversions, utterly important, converting one unit into another unit. Centimeters into meters, but also density into mass, or, for instance, inches into kilometers. Okay? Those kind of conversions we have done many times over, and we should be able to do that on the exam. Atoms and isotopes, we talked about the basic architecture of an atom, isotopes, ions, and so forth. And we should know something about the orbital and where the electrons are, remember? And how many electrons a certain atom has, how many protons it has, how many neutrons. So the basic architecture of an atom is something that's part of this exam, as is naming these atoms, making molecules from them, and naming their ions properly. Knowing the charges of the ions, and knowing the difference between a polyatomic anion and an elemental anion, for instance. Okay? Then we started to do some calculations with molecules, atoms, and ions. Namely, we started to determine the molar mass of these guys and mass percentages of elements in compounds. Okay? These calculations are part of the final. Then we looked at chemical reactions. So we have molecules that are actually engaging into a chemical interaction, and there are reagents and products. And we should be able to balance such a reaction and come up with the right stoichiometry. Why is the stoichiometry so important? Because we have to be able to determine mole ratios between things. Mole ratios can be used to convert one type of compound into another type of compound in terms of how many you have. Okay? So we need to be able to do the mole ratios properly. Stoichiometric coefficients give you the mole ratios. Molarity, and again, stoichiometry in solution. We've done that. We've looked at many compounds that are dissolved in water and then react in aqueous solution. Okay? The molarity is an expression of concentration, and along with it, we should be able to calculate, for instance, how many ions of a particular kind there are in a solution. Okay? If I throw aluminum chloride into a bucket of water, you should be able to calculate the number of chlorine ions in it. Okay? If you dilute it, put another liter in there, you should be able to calculate the number of chlorine ions again, or calculate the new concentration. Those are very standard calculations that we've done. It's part of the trial. And then finally, three types of reactions that we've wrestled with: precipitation reaction, acid-base reaction, and redox reactions, as examples of very important chemical reactions. There are more types of chemical reactions, but these are three main ones you should be familiar with. Dealing with your stoichiometry, being comfortable with the naming of the compounds, will set you up for a successful Chem 1A series after this class. Okay. Now, I'm going to say a few more words, some details about exam taking, and then I'm going to say a few more words about redox, just to wrap that up. Here's a kind of a snapshot of an exam 2 years ago. Here's a question about in terms of molarity. We're not going to look exactly at how this is answered. I'm going to tell you that show your work, because we are grading your work. Okay? In this particular question, you are asked to calculate the volume, okay, of a solution. And there's some details here. But you have to do the first thing you always have to do is calculate. You have to determine how many moles of the stuff do I have. Always, you want to know how many moles you have. And once you know the number of moles, you can easily calculate either in grams or in molarity and so forth. So that's the first step. You have to determine the number of moles. Check. That check means you're on the right way. And that means you get points. Okay? Then you have the number of moles. You have to do something correct with it. Okay? You have to convert that, in this case, to volume. The molarity is given is a ratio. Namely, the definition of molarity is number of moles over volume. That means if the volume is unknown and the other two are given, I can calculate the volume. That's exactly what you have to do here. And that's the second check. If you know how to do that, you get points. In other words, you get points for these steps. So for instance, 5 and 5, total of 10 points. The final answer actually is not even the most important. Okay, so even if it's completely wrong, you still get points for doing this correctly. The methodology, the grading methodology, takes a lot of time for us to do that, but we think it's very important. Okay, so we go through all the calculations of all you guys, all 300 exams. We go through all the questions and see if there's something correct in there. The better, the more, okay, let me put it like this. If you want to help us, and this will help you to get more points, be clear about what you're calculating and what steps you take. If you can write it down like this, for instance, this example, where I say exactly what I'm trying to do in each step. I'm going to calculate the number of moles needed and so forth, conversion to gram. I'm going to just explicitly write out what I did. Then the grader can see, oh look, I mean, this is very nice. This 1, 2, 3, 4 steps, beautifully laid out. Maybe a little mistake here and there, but at least the person knows what he or she is doing. This greatly helps us grading and helps you getting more points. Because if this is all messy and jumbled up, we have a very hard time giving you partial credit. Okay? So, check, check, check. We can give you more points. That's the bottom line. It's completely fine to do this first on the, use the blank page. First write out the, what you think the answer should be, and then reproduce the answer neatly and nicely with the correct steps in the blank so that we're actually looking at. Just one tip. You don't have to do this. I'm just telling you it's an option that makes life a lot easier for us. Okie dokie. Keep it in mind. I'm going to wrap up the topic of redox very briefly by the following. We know what redox reactions are by now. Redox reactions are reactions where there's an oxidation step and a reduction step. Something is losing electrons, something is gaining electrons. Here's an example. In this particular case, I can split this into half reactions. Namely, the iron is losing electrons, so that's the oxidation step. And the copper here is gaining electrons, so that is the reduction step. So I can write this in the net equation in the following way. Forget about this sulfate. It's a spectator anion. It doesn't do anything. It doesn't partake in the reaction whatsoever. Everything is aqueous, so I can just get rid of it and just write this. It's very easy to see in this case that, look, this guy is changing to 2+. This 2+ copper is changing into solid copper, which has oxidation state 0. In other words, this is the reduction step, copper, and that is the oxidation step. Both things take place at the same time. Okay? So you can nicely see in this way of writing that the electrons lost by the iron have been eaten up by the copper. Effectively, the only thing that happened here is that 2 electrons lost by the iron have gone to the copper. Okay? So there's homework due this week, okay, Friday, as usual, at 11 o'clock. It's about redox reactions in all the conditions that we have considered, namely just normal redox reactions in solution, two flavors, acidic and basic conditions. Okay? So here are a couple of Sapling questions that have come up during office hours that I'd like to just quickly go over. Hopefully it will clarify a few things. So I'm just going to see if we can lift this thing up. That could be challenging. Small screen up, down. How do we get this thing on working? Okay, perfect. So let's look at the first one, because the Sapling does things slightly differently than we have talked about in class, and so you should know that. So the first one is O2, and then 4 coppers, and then copper oxide. So you see, first of all, what Sapling doesn't do so nicely, which I really don't like, is there's no physical states. Okay? That's not nice. Don't do the same thing on the exam. We have to write physical states because actually it is somewhat confusing in some of the cases in Sapling, what really is going on. So in this case, what they want you to do with the first equation is to write half reactions. And the problem is copper oxide this thing actually is a solid. And we have said in class that you should keep it as a solid. Okay? But Sapling doesn't stick to those rules, unfortunately. So what they say, fine, consider this as an ionic compound, and in effect, I have two ions. Namely, this thing is oxygen, oxide, always 2 minus. And this copper, because this is 2 minus, there's 2 of them, must be copper plus. In other words, this is copper 1, oxidation state 1. This is oxide. Standard oxide is always oxidation state 2 minus. Okay, so now I can write the half reaction, because really what you have to do is, in this case, oxygen, O2 turns into O2 minus. Okay? And copper, which was oxidation state 0, turns into copper plus. And I want you to balance these two guys relative to one another. So we can see which one is the oxidation, which one is the reduction. This, in fact, is the reduction step, because this is 0, this is 2 minus, so it becomes more negative. That means it has taken up electrons, so this is the reduction step. This is the oxidation step. Indeed, this one is losing an electron. So some electron has to appear here, and some electron has to appear there. But to do that, I have 2 oxygens here, 1 here, so I need to put a 2 there to balance the oxygens. There's no need to put waters there. There's already oxygen there. Okay? There's already oxygen there. You just have to balance out the oxygens. Then when doing so, I have 4 charges there. Okay? In total, 4 minus. That means I have to balance that out. Okay? So in this case, I have to add 4 electrons to that side. We have 4 minus on each side. Okay? This is the reduction step. That's right, because in the reduction step, it should appear on this side. Copper, the elements are already balanced, the charges are not. I have to add an electron here. Okay? So that's it. The only thing I have to do now is to make sure that they're balanced relative to one another. Sapling wants to do that. You can do that by putting a 4 there, a 4 there, and a 4 there. 4 electrons in each case, and this is the final answer. Okay? Let's do the second one. Funny one. Funny one. And not something you can expect on the midterm. On the final. So it's very much an exception, but I just want to show it so that you don't get stuck on the final. The question is, you have to balance this equation. Okay. Plus copper again. Yeah. Copper again, 2 plus. And it generates S4O6 2 minus plus Cu plus. Okay, so what I'm going to do, I'm going to split this again in 2 steps. I'm going to write down copper 2 plus. I'm going to go to copper plus. Oh, this one has taken up an electron. Okay, so electron plus this gives me that. This is the reduction step. That means the other guy is the oxidation step. Let's just put it down. Okay. Now this is indeed an oxidation step, but there's something very funny going on with this particular compound. If you try to find the oxidation state of sulfur, you are in for a big surprise. Okay? The oxidation state of the sulfur here is 2.5. That doesn't make any sense. Okay? And it doesn't make any sense because it is a very particular compound where the 4 different sulfurs actually have different roles in different oxidation states. So this goes way beyond what we should know at this point, and is also not relevant for our discussion. So I'm going to tell you what you should focus on with these kind of questions. You balance the elements. You can do that quite easily by putting a 2 there. Okay? So now I have 4 sulfurs, 6 oxygens. That's the same as here. But in doing so, I haven't really balanced the charges because 2 times minus 2 is minus 4. I have minus 2 here, so I need to add 2 more. There. Okay? So now it's balanced. This is the oxidation reaction. It is indeed an oxidation half reaction because I'm generating electrons, products. To balance them relative to one another, I have to multiply this whole thing by 2, 2, 2, 2. And now I can add them up. And the final solution, I can put it in here, 2, 2, 2, and that's it. Okay? That's the answer for that. Let's do the final one too. Why not? I'd like to do this also because I want to show you that even though these questions may seem laborious, if you know your stuff, you can just simply write as if you write a letter to your mom, okay? And in that kind of case, you can solve this problem. It is straightforward application of the rules that we've dealt with. So here, this is again a permanganate anion that is undergoing a redox reaction. So I'm going to write down permanganate. It's changing into 2 plus. I can quickly look at the oxidation states here. This is 2 plus, evidently. This whole thing has to be minus 4 times minus 2 is minus 8. This must be plus 7. Okay? If you don't know how to do that, teach yourself how to do it. We've done it a lot of times. It's essential you're able to determine the oxidation states of these things. Namely, oxidation states of all these guys added should add up to minus 1. This is minus 2, there's 4 of them, is minus 8, plus 7 equals minus 1. This must be plus 7. It shouldn't take you a lot of time. Okay? Linear algebra should take you about 10 or 15 seconds to figure it out. Don't lose time on that. So I'm going to balance this equation. What do I have to do? This happens in an acidic environment, let's say. O4, I need to add 4 waters, but I have added also 8 H plus if I do that. So I put that on the other side. Okay? And now I have balanced all the elements, but I have not balanced the charges. Now I can tell you what the charges should be without even looking at the charges on each side. I can tell you that since this is 2 plus and this is 7 plus, it needs 5 electrons. Right? There have to be 5 electrons on this side. Because it's goes from 7 plus to 2 plus. So that's a check. But I can also do it like this. The whole total charge on this side is 2 plus. The total charge on this side is 8 plus. Okay? Minus 1 is 7 plus. And I need to get to 2, so I need to subtract 5. That's exactly these 5. Right? So either way, it doesn't matter how you get there, but do this consistently correct. Okay, then the second one. So this is the reduction because this one eats electrons. This guy turns into NO3 minus. What's going on here? Let's look at the oxidation states very quick. Whole thing is minus 3 oxygens, minus 6. This number is plus 5. What is going on here? This thing here is the nitrite anion. Okay? And H plus is added. So this whole thing here is oxidation state has charge minus 1. Oxidation state minus 2 times 2 is minus 4. Plus 3 is minus 1. So this is plus 3. Okay? The oxidation state of the nitrogen is changing here by 2. By 2. Okay? So I know 2 electrons have to appear here. I can already tell you that without looking at anything else. So let's see if that actually works out. First of all, there's 2 oxygens here, 3 there, so I have to add water here to balance the oxygen. By doing so, we introduce 2 extra hydrogens. There's already 1 here, but it's 3 in total. It's plus 3 H plus. Okay, now let's look at the charges. Did they add up correctly? No charge on this side. Okay, no charge on this side. That means it has to be no charge on this side. This is minus 1. 2 electrons, minus 3. 3 plus, correct. Right? So, balance the charges, balance the elements. Now I have the two reactions. This thing has 5, this thing has 2, so this whole reaction multiplied by 2, this whole reaction multiplied by 5, and then you can add them up. And that's it. So you can do that for yourself, and then cross out the H pluses and cross out the waters. Okay, so that's just a little detour, but you see, you can just write this, add waters, add H plus, balance with electrons, and this can be done relatively quick. Right? And doing it several times, like doing the homework, is really helpful in getting comfortable with these kind of questions. Typically, people do pretty well on Redox on the final. So I'm pretty confident you guys will step it up. Okay. Let's rewind and go back at the very beginning when we talked about dealing with numbers and dealing with units. One of these things is writing numbers correctly. Significant figures is a way of writing numbers correctly. And we should do that. We should just do that. So, if you do that, make sure you discriminate between multiplication and division and addition and subtraction. They have different rules. Multiplication and division says you have to give the number that you are calculating the same number of significant figures as the least precise number in the calculation. But that rule is different if you add and subtract, because in that case the rule holds that your answer should have the same number of decimal places as the least precise measurement in the calculation, or the number with the least amount of decimal places dictates how much you get in the answer. So let me quickly give you an example of how that plays out in practice. Let's look at the following. Calculate the mass of magnesium here, 0.643. Well, if you do that, you go into the periodic table and you look at the molar mass of magnesium, and you'll find 24.305. This number comes from the periodic table and has 5 significant figures. Okay? This is not the limiting factor in my calculation. It has 5, this one has 3. So the final answer, since this is a multiplication, should have also 3 significant figures. Okay, I think we can all do that, and most of you have done that correctly on exams. Now, there's a situation where you may wonder what to do. And that happens when you, for instance, have a calculation that involves both multiplication and an addition of some sort. For instance, calculate the total mass of this much magnesium and this much chlorine. Okay? So what you have to do is, well, I have an answer here already, 15.6. I do the same thing for chlorine. I take the number of moles, I multiply that by the molar mass of chlorine, that is 35.453. It gives me this number here in grams. Okay, so that is the answer, but this should be given in 3 sig figs, because 1 to 3 is the least precise measurement in this particular question. And so the answer here is 1.61. I have 2 numbers. These 2 I have to add up. So what I do here is I first finish the number that I'm getting to, and I have to add up. And I'm rounding this because this multiplication step is over now. And I have to make sure that when the number rolls out of the multiplication, it has to be a proper number that means something. It means something if it has the right number of significant figures. So what I'm doing, I'm taking this as the input in my addition. So I'm going to add this number to it. These are 2 results that are added up. As you can see, this is what your calculator says, but you have to realize that this number here has 1 decimal place, and hence you should also have this number in 1 decimal place. That is the rule for subtraction and addition. So the answer is 70.3. It has 3 sig figs, not because it has 3 sig figs here and here, but because the addition says that the final number needs to have 1 decimal place. Okay? So first complete the multiplication and division, then add them up and use the rules for each operation. Okay, now let's do an example of the kind of calculation that we have done. Let's determine the mass percentage of each element in this particular formula, this particular molecule. So let's do that. Here's the chemical formula of this compound. From this formula, I can calculate the molar mass, right? 14 times the molar mass of carbon, 12 times the molar mass of hydrogen, and 3 times the molar mass of oxygen gives me the molar mass. What I do then is 14 times the molar mass of carbon divided by the total that I just calculated times 100, and you get a percentage. What is the number of sig figs in this answer? Well, it is determined, this is a division and a multiplication, hence the number with the least amount of sig figs is determining the answer. And in this case, that is this number right here. Okay, this one has 4. This number comes from my table. If this number would have 5, then this would be in 5. You would have 3 places after the decimal point. Okay, 3. But because this is in 4, your answer is going to be in 4 sig figs total. Hydrogen, let's say, for instance, that the table you get the information from has 3 sig figs for this number, the molar mass of hydrogen. Then your answer should also be in 3. Okay? If this was 4, then your answer was in 4, and you get 5.30 something. There's one more digit in that case. Right? And, the same for oxygen. In this case, there's 4. That means the answer should be in 4. But maybe this is an example not so well chosen. If this is 4, then you get 3 places after the decimal point, right? 3 digits, which is 2 here, 2 there. So it doesn't mean these calculations are independent of one another. This can have 3 digits after the decimal point. This one can have 2, this one can have 2 at the same time. So you don't have to kind of line them up for some kind of symmetry reason. That's not what dictates sig figs. You look at each calculation separately. Yeah.
This 5.30, is that 2 sig figs?
No, this 0 is after a decimal point. This is significant.
Oh.
Yeah. Conversions, people. You have to be able to construct the right unit factors for converting one unit into something else. And one of the most, I would say, involved calculations are calculations of volume, okay? Because you have to multiply length to the power 3. Okay? So for instance, here you have a box. You have to calculate the volume. The box is given in inches, as you can see, but I have to give my answer in liters. Everything okay? So liters is decimeter cubed. Right? That's the definition. 1 liter equals 1 decimeter cubed. So I have to go from this inches into something that is metric. And so you want to go probably from inches to centimeters, then centimeters to decimeters, and then decimeter cubed. So what we can do this in a variety of ways. This is one way to do it. These are the 2 definitions that you need. The relation between inches and centimeters, and the relation between liter and decimeter cubed. So, for instance, I can convert each length separately. That's a possibility. This is 1.5 inch. I can convert that to centimeters by multiplying by this unit factor. 1 inch, 2.45 centimeters. This one goes on top, this one at the bottom. Inches is crossing out. I get my answer in centimeters. Everything between parentheses here now is in centimeters. And I can do it for each of the lengths that I'm multiplying. For instance, width, length, and depth. I do that for each one. I do each of these guys, I can do the conversion on separately. That's completely fine. I could also have done it in one step, of course. I could have multiplied these numbers and then have this conversion step raised to the power 3, which is exactly the same calculation. Because effectively, that's what you do here. 1 conversion, 2 conversion, 3, all multiplication signs. You basically raise this conversion to the power 3. Right? That's exactly the same operation. Whatever you prefer is fine. These things are equivalent. The answer is 446 centimeter cubed. Why is it cubed? Well, you have 1, 2, 3 centimeters multiplied, it becomes a centimeter cubed. Right? The next thing I have to do is relate this to decimeters. I convert that by using the conversion between centimeters and decimeters. 10 centimeters to 1 decimeter. 1 decimeter equals 10 centimeters. Centimeter goes at the bottom. This one goes on top because I go from centimeters to decimeters. And raise to the power 3, so the unit factor also goes to the power 3. Okay, so that means you can convert this number now to decimeter cubed. And 1 decimeter cubed equals a liter, so you can just replace decimeter cubed by liter, and this is your final answer. I'm going to put that in 2 sig figs, because this one has 2 sig figs, this one too. Okay? So be familiar with this kind of calculation. If you are on the exam and you see this volume conversion and you have no idea what to do, then you haven't prepared sufficiently. Okay? It will be probably something like this on the final because I want to see if you can do this. This is how it works. This is one way in which you can solve the problem. Math. Throughout this class, we have used different formulas. The main formulas from which you can derive everything else are the following. Density equals mass over volume. Molar mass equals mass, total mass, over number of moles. Okay? That's how you calculate the molar mass. Or you can also say, you can circle this through, right? You can basically put this mole right here, number of moles equals total mass divided by the molar mass. That's the same. And the definition of molarity, which is the number of moles of the solute in liters of the solution. Almost all calculations make use either of this, or this in one way or another form. Okay, so typically something is given, two variables are given, and you calculate the third. Be it mole, be it liter, or molarity, it doesn't matter. These relations can be used and rotate through to calculate any of the missing variables. Right? This is really all the math there is to it. It's either division or multiplication. That's it. And your relations will tell you what it is. So don't flip things. Again, there were lots of situations on the last midterm where people simply guessed if it was a multiplication or division. If you do that, you have 50% chance that you do it wrong. Okay? Two ways to avoid it is the following. Think about these relations, and you're able to tell yourself, convince yourself what you have to do. If that is not enough, look at the units. The units should cross out properly. Okay? If they do not, you probably made a mistake. So look at your approach carefully. If you know what to do, of course, no issue. But if you're stuck, you feel like, I don't know what to do. Multiplying, dividing. You have to use logic. Never, ever guess. Because the chances are pretty high that you make the wrong guess. Okay? This is not how we do science. In science, we can guess. If you are in a hospital and your advisor says, give this person this many molecules of this drug, and you have to guess whether you have to multiply molarity or divide, you are in big trouble. If your guess is wrong, patient may die. Okay? You don't want that on your resume. You'll never find a job again. Okay? So these things are things you can avoid by just staying calm. And there is all these things are logic. There are no blurry lines here. They are not there. The blurry lines are only in your head. Get rid of them. Okay, an example of a quick calculation could be anything. I have 1.2 liters of calcium sulfate solution and has a certain concentration. Now the question could be, for instance, calculate how many moles you have, or how many grams of this stuff do you have. How many grams were dissolved in this solution? How do you do that? Well, I want to know how many moles. I know liters times molarity equals moles. Boom, boom, boom. Okay, this is something I've done so many times that I trust that it is okay. Liters times molarity equals moles. If you don't believe that suddenly, okay, it may happen. Suddenly you may say, oh, hold on a second, I don't believe that anymore. And you can always say, look, molarity equals moles over volume. That's the unit of molarity. Molarity is moles over volume, M over L. L is here, L is at the bottom, L crosses out, your unit is going to be moles. That's called dimensional analysis. You can use that unit trick to figure out if you're doing the right thing. Always check that if you have time. If you know the number of moles, you can do a simple multiplication with the molar mass to find the amount of grams of calcium sulfate that were dissolved in this particular solution to get to this concentration. Number of moles times the molar mass equals your answer in grams. If you forget about this, look at the units. Mole here, the unit of molar mass is grams per mole. mole crosses out, your answer is going to be in grams. Right? Another one, 1.2 liter solution has a density. This is not given in molarity, but in density. Is that a reason for me to panic? Because I'm used to working with molarity, and suddenly the concentration is given in density, kilograms over liters. No, it's not a reason to panic whatsoever. Okay? I can do exactly the same calculation because I can calculate how many kilograms I have in solution. I know the relation of density, liter and mass. Okay? So that means that if you multiply volume with density, you should get an answer in kilograms. The unit of density is kilograms per liter. So if you multiply this with liter, L will cross out, and your answer is going to be in kilograms. So here I have a measure of mass, thank you very much, and the measure of mass can be related to how many moles of that stuff you have, for instance. Okay? All right, so this is again molarity. It was an important quantity, and we should be able to do quick calculations with it. This is a typical question. This is a question that goes on the midterm, the last midterm. Okay? I would say probably 50% of people did this incorrectly, and you shouldn't do that again. Okay? This is a very standard and very practical situation. You have a certain volume of a solution, 1.2 liters, and you have to add a certain amount of sodium phosphate. Actually, sodium phosphate is the main ingredient of a very important buffer system that people use in the biology lab all the time. Okay? It's also a very important buffer in medical sciences. So this is not a ridiculous question. 5 grams of that stuff dissolved in 1.5 liter. Your advisor wants to know, what is the molarity of that? Okay? The molarity of sodium ions, he wants to know. Okay, so you have to realize that, look, sodium phosphate is this. Phosphate is 3 minus. You need 3 Na plus to create a neutral compound. So Na3PO4, that is sodium phosphate. If you dissolve that in water, what you get is 3 sodium ions, 1 phosphate anion. In other words, with each 1 mole of this, you generate 3 moles of sodium. So, 5 grams divided by the molar mass of sodium phosphate, okay, gives you the number of moles of sodium phosphate. This is the amount of sodium phosphate in moles that has been dissolved in 1.2 liters. But it does not tell you what the concentration of sodium ions are. Yes. So, you can take this and divide it by liters, that gives you the molarity of sodium phosphate, but you have 3 moles sodium ions for each 1 mole of the compound. So you have to multiply that by 3. That 3 should not come as a total mystery to you. Okay? This is nothing mysterious. There's no other way this can be. Because there's 3 sodium ions per 1 mole of the compound. You have to multiply this by 3. You get 3 times as much sodium as you have this. As you have sodium phosphate. So the answer is in this case 7.2 times 10 to the minus 2 moles per liter. Give your answer in the correct number of sig figs, preferably in scientific notation, and with a unit. Please add a unit so we know what you are talking about. Moles per liter is, in other words, is basically the unit for molarity. So you have to put a big N there. Okay. 2 more minutes. Naming compounds is something we have to be able to do. Here's one. What is that? Beryllium sulfide. Yep. Beryllium, by the way, is 2 plus. Sulfide is always 2 minus. Good to know. Right? What is this? Phosphorus tribromide. Tribromide, because this is a covalent compound, a molecular compound. This is not an ionic compound, so you have to tell the reader exactly how many anions you have in this case. How about this? Ammonium hydroxide. Yes, ammonium hydroxide. This is the ammonium cation. If the H plus splits up, you get NH3. which is a molecule. That's the ammonium molecule. The ammonium molecule we have seen many times. Ammonium is a molecule. If you add a proton to it, it becomes ammonium. NO2, what is that? Nitrogen dioxide. Nitrogen dioxide is not nitrite. Why not? Because there is no minus there. Polyatomic anions always have their charges indicated. Always. Some people ask me, do I have to write down the charges of the ions? The answer is yes! Is that clear? Yes! Always add the charge of the ion. If you don't do that, you just write down something else. For instance, if you forget if this was nitrite and you forget the charge, it becomes nitrogen dioxide, which is completely different. What is this? Sodium nitride. Sodium nitride, because this is an anion that has 3 negative charges, right? Let's do one more. What's that? Aluminum oxide. Yes, it's aluminum oxide. But do I have to say how much? Do I have to stipulate the oxidation state of aluminum? No, you don't. Because aluminum is a type 1 metal, not a type 2. It only has one oxidation state, which is 3+, ammonium oxide. All right, see you on Friday for the second session of the review.